Our last portion here on vectors here, 10.8c, we're going to add and subtract vectors now in terms of those rectangular coordinates. We looked at their components in our last part of our last video, where we had an I portion and a j portion, and the I represented the x and the j represented the y. Well, this is going to be pretty straightforward too. So we've actually already seen this. When we add vectors together, we're just doing it now in terms of I and j. So what we saw when we added vectors is we added the x parts, we added the y parts. Well, same thing here. So now we just have it in terms of these I and j components. So we're still adding the x portions, we're still adding the y portions, and we get this. Okay, now this is also another idea we've seen multiple times. So if we had a vector here, let's make it a position vector starting at the origin. Well, we would have some vector x, y. Well, we've done this before. Let's imagine there was a right triangle there, and there's some angle there. Well, what we could see is the cosine of theta would be the x portion of the vector over the hypotenuse, and our hypotenuse is the magnitude. So we're doing exactly the same thing that we've done. We've seen this before, we've seen this before, just because you could create a right triangle. So if you wanted to solve for x, we've done this exact same thing before. We would send the hypotenuse up to the other side. So here's a way to express x and y in terms of their magnitude and direction. So we could just substitute, if this is a vector, in terms of its x and y components. If we chose to, we could represent them in terms of their magnitude and cosine and their magnitude and sine. Okay, let's take a look at one of these. So they've told us the length is 7 and we have an angle of 135. Well, the length is the same thing as the magnitude. So I've got a magnitude of 7. So let's find the different components here. I've got the v portion of this, or the magnitude of the x portion is cosine of that 135. The y portion is the sine of that 135. So pretty straightforward. We're just crunching it down, solving these. So cosine of 135 is negative radical 2 over 2 multiplied by 7. Sine of 135 is radical 2 over 2, and we multiply that by 7. So here's my components. Now this should have our I and our j in there. Yeah, they left that out. So we have our I and our j in there to represent that this is the x portion and this is the y. Okay, so let's do this again. We've got a vector here that's coming up to 3, 5. So let's first of all, we want to find the magnitude of that vector. Well, that's just, so 3 squared plus 5 squared. It's just the Pythagorean theorem again. We've done this many times. So that's the square root of 9 plus 25, so the square root of 34. So the magnitude of v is the square root of 34. Okay, so we have our magnitude, and now what about our angle? Well, we are looking for this guy right here. Okay, well, we can do this. The x portion is going to be cosine of that angle, and the y is going to be the sine of that angle. So what we need to do is we have our 3 here, a 5 there, and our magnitude is 34. So we don't have the actual angle, but we know how to handle that too. If I have a complete triangle, I know the value of cosine of theta. So this is going to be radical 34. That's the magnitude we found. Cosine of theta would be adjacent over hypotenuse. It's going to be 3 over the square root of 34. So you see that's going to cancel down and nice and easy be a 3. Now we know the magnitude of v down here is the same. Now sine of theta, we don't have the angle, but we have a complete triangle, so it's opposite over hypotenuse. So 5 over the square root of 34. That's going to settle down to be 5. Okay, so what's our final vector here? 3i plus 5j. All right, now I was looking up dot product here, trying to find an intuitive explanation of this, and I don't really think there is one. What's happening here, or at least that's in the scope of this course. So I'm going to leave the proof to the book or the internet because it was beyond what I think we can cover here. It doesn't seem intuitively clear, but this we've learned. Each of these are unit vectors. So a dot product is going to take the two unit vectors and it's going to show how they relate to each other. We can find the angle here between by taking the dot product of the two unit vectors. Again, I don't find this intuitive, but if we wanted to find the angle between two vectors, what we can do is we can take their dot product. We can multiply together their two unit vectors. And what that creates is the cosine of the angle that's between them. So we saw what a unit vector is. Take the magnitude and divide the original vector by the magnitude. Now here's what a dot product is going to do. A dot product is going to multiply the x components and the y components, and then it's going to add them. So again, I'm sorry I don't have a real intuitive explanation for this, but what we're going to be doing here is we really are working with the components of the x and the y direction. But again, the scope is beyond at least my ability without really digging into this because it didn't make a lot of intuitive sense. So let's find a dot product. So a dot product is just going to multiply the x components and the y components here. And then once you've multiplied the x and y's, you're going to add them together. And so we get 33. So that's the dot product of two vectors. Now we want to find the angle between them. So what we're going to do, we're going to use this formula here. The angle between them is related by multiplying, taking a dot product of their unit vectors. So first what we need is their two unit vectors. So yeah, first it wants just the regular dot product. So we saw that again. We're going to multiply the x components and the y components and we add them up. And there's a dot product. Now, let's take a look. We're going to find the angle between them, and we know they're related by multiplying together their unit vectors. So, there was a mistake on here. Yeah, this shouldn't be a plus. These should be parentheses. Okay, so if I have these two vectors, do you remember how we'd find their magnitude? The magnitude of v, which was which? Okay, so the magnitude of this one, the magnitude of v1 is going to be 25 plus 4. So square the x component, square the y. So it's going to be the square root of 29. The magnitude of v2 is going to be 9 plus 49. So just squared the x component, squared the y component. So I've got the square root of 58. Okay, so what we would do is to create a unit vector is we would divide it by the length. Our unit vector is a vector of length 1 that's going in the same direction. So what we said here is that we could just take that original vector and divide it by its length, which is its magnitude. So I found the two magnitudes, and now I'm dividing each of the vectors by their magnitude. So this is the x component, this is the y of v1. This is the x component, this is the y component of v2. Okay, now we've done that. So now we're going to take a dot product between these guys. So now we've created this. Their dot products multiply the x portions, multiply the y portions, and then add up the answers that you get. Now this is not, these are some pretty crazy numbers here, but we're going to get this if you use a calculator to get all of this. Now what we're saying here, and again, I know this is not intuitive, but magnifying the two unit vectors together has a relationship, the dot product of their two unit vectors multiplied together gives us a relationship with the angle between them. So we've got the cosine of theta is equal to 0.7071. If I find that inverse, I find the angle between them is 45. Okay, so let's do this again. We want to find the angle between two vectors. So what we want to do is we're looking for this cosine of theta is going to be the dot product of their unit vectors. Okay, so let's find those. So we find the magnitude by the Pythagorean theorem. So u would be 9 plus 16. It's going to be 20 square root of 25, and we want the positive value, so the magnitude of u is going to be 5. So we're just doing the Pythagorean theorem. It gets us the magnitude. So this is going to be 25 plus 144, or the square root of 169, which is 13. Okay, so I have my two magnitudes. Now, we're going to divide them by their magnitudes. So u divided by his magnitude is here. V divided by his magnitude is there. Now, the dot product says multiply the x components, multiply the y components, and then what you get, you add them up. So we do that, we get 33 over 65. Now, this has created this relationship. This tells us that the relationship between the angle is the cosine. The cosine of theta equals 33 over 65. So we inverse cosine that, and the angle between them is 59.5. Okay, now there's one crazy word problem here. I thought about skipping this, but I'll just take you through it real quick. Here's what they're saying. A plane is heading 140 degrees from north. He's heading this way, and he's going at 200 miles an hour. But there's a wind pushing him. Wind is coming down at 16.2. So the wind is pushing him. So what we want to do here is, oh yeah, he's going 200 miles an hour in this direction, but the wind is pushing him. So what we want to know is this green arrow. This is going to be his real speed because he's getting some help from the wind. Can you see that? He's going 200 miles an hour, but the wind is helping him. So x is going to represent this third side of this triangle that we've created is going to represent the speed of the plane. It's going to be bigger than 200 because the wind is helping him go in this direction. So I've got two sides of this triangle, and I want to find the third. Now here's the other trick that may not be obvious to you. So do you see we've got two parallel lines here? And so we've got this line cutting through a parallel line. I don't know all my trigonometry terminology or my geometry terminology. What do they call that? Oh yeah, alternating interior angles. So if we run through a parallel line with this line, the alternate interior angles are the same value. So this is 140, and in this triangle over here, that angle is also 140. Okay, well, what do we have? Well, we have two sides of a triangle and the angle in between. We don't have a complete ratio, but we have two of the sides and an angle, and we want the side opposite there. You know what we have? We have the law of cosines. We have two sides, and we have an angle in between them, and we want the side opposite that angle. That's the law of cosines. So we crunch this down, and we find we get 212. So this green arrow is 212, and it represented a speed of the plane. So this wind is helping the plane go 212 miles an hour instead of just the simple 200 you would think. So we're going 213 miles an hour. Now the bearing is represented here. Which one was the bearing? Oh yeah. So the bearing here is going to be this original 140, but plus this angle alpha. We want to find this angle alpha. So that's just a missing angle inside of our triangle. So let's use the law of sines because we now have a complete ratio. This is the ratio that we just completed. We had the angle, we had the side across from it. Let's find the value of alpha, which is how the wind has pushed the plane off his initial course. Okay, so sine of alpha over 16.2, we crunch this down, we get 2.8 for that alpha. So the plane was heading this direction, but the wind is not only helping him go faster, but he's also pushing him down. He's pushing him off course by 2.8 degrees. So if we want the original bearing from north, it was the 140 plus that additional little piece there. So 140 plus the 2.8. Okay, again, so here's this one, and just real quick, I don't think I would do this to you, but so we've got a triangle created here. The plane was going 200 miles this way, the wind's blowing and pushing him down this way. So we found the speed, this green line here. We found that speed by using the law of cosines. We have two of the sides, and we know this 140 must also be the same angle as inside of this triangle. So the law of cosines helped us find this side here. Now we needed this angle here. How far off course are we being pushed? So we used the law of sines because we now had a complete ratio. Okay, hope that made some sense.